three different modes. The first one is called compare. And I think it's on the website. We have a lecture and have a very short tutorial on it. I think it's lecture 11 on Dr. Costin's website. And I also have a one web page on my website. It's compare mode. We don't have a lab on it. We don't even have assignment on it. So be careful. But you still have to understand what's going on. Okay? It's timer 1. It matches the register value. Then it does three different things. It could be toggle. So it doesn't matter what the current state is, it's going to toggle it. Or reset. Or set. Remember we had an example on that website. We didn't download it to the microcontroller. However, we talk about that. We have to change the mode. So the first time we get into it, if it is resetting, we immediately change it to set, then do something. And the next time it gets into there, it's detecting the set, then we have to reset it. Doesn't matter, that code is not important, but what you need to know is how which one is matching with what. So it's timer 1. You can definitely use timer 1 to match with that CCP register, CCPR, right? CCPR1, I think. Whenever they match, it do these actions. Remember, keep in mind, it's a different mode, so the PWM mode is different. And this is the mode we use in lab 5, in lab and lab 5. So if you see a problem saying it's using the compare mode, you have to use the matching and all the actions mechanism over here. I'm gonna go through some of them in a bit. And for the PWM mode, is something we'll have to spend like 20 minutes today to talk about. And there's another one, it's called capture mode. We don't have any examples, no labs, no examples, no assignments. So you can basically ignore it as of now. I'm not sure if there's any examples in the future lectures. I haven't been there, and haven't tried any of the examples on the website, but you can ignore this part for now, okay? So now let's talk about this one, important. So long story short, the PWM mode has two important registers. It's called PR2, for example, or PRX. Another one is called CCPR. Remember, CCPR is not CCP. No, CCPR is a CCP register. CCP is a pin. That's a pin. That's a physical pin. It's output or input. It's output. It's a pin. Okay. CCPR has CCPRH, CCPR1 usually, or CCPR1L. So it's totally 16 bits for these two CCPR registers. Pay attention, okay? There's an R here. If it's an R, it's a register. If it's a P, it's a pin. It's a pin. PR is a period. It's a period register. And it's an 8-bit register. So that's the PWM mode. Okay? So it's usually using timer 246. 2 or 4 or 6. We have been using timer 2 all the time. Timer 2 has a register. It's an 8-bit register. And there's a frequency toggling it. And that frequency is called FOSC over 4 with a 1-to-1 prescaler. Okay? Important. Very important. The digital designer who knows how to write Verilog a lot, designed a little 2-bit and concatenate it with that 8-bit to form a 10-bit timer. Okay? And this single bit here, let me give example first. Okay? 2 digits, and here's another digit. All right? 0, 0, 0, right? I'm start counting. 1, 0, 0. 0, 1, 0. 1, 1, 0. What's next? 0, 0, 1. So see, this bit is being toggled. How many times faster than this bit?
4 times.
4 times faster. Why? You can consider this bit is whatever here shifted to the left by 2 bits. So if you shift to the left by 2 bits, you times 4, right? So this has been toggled for 4 times, and this one starts toggling. Okay? So this bit here, that's 2 bit over here. These 2 bits and these 8 bits for the timer tool you have been using is forming a 10-bit timer. And usually you don't use it until you see this PWM mode. You have to use it. So if this one is a regular frequency you have been using, right? What's the frequency? 16 megahertz. So this is 16 megahertz, right? What's the frequency here though? Yeah? So in that case, the conclusion across this whole semester, what is this?
64
Keep in mind, all right? Keep that in mind. Let's
So
do this.
the actual timer when it's working in the board is utilizing the 64 mega timer, but it's just padding with those extra 2 bits that it's counting.
Yeah, you do have a 16 megahertz. That's the fastest frequency you have on the chip.
Gotcha. And it's
So I
counting
think,
it
yeah, and it's being divided by 4 times to support other
Gotcha.
the CPU and everything else. So you got higher speed whenever you need it, but you don't use it all the time. What's that?
What is the PR2 register for?
That's a period register. I'm gonna go through that now. Okay, don't worry about that. I'm gonna talk about that now. Okay. So, if we include a prescaler in here, can we just write this? Pre is prescaler. This is 16 megahertz divided by the prescaler, which is the frequency toggling this bit. Toggling this bit. Okay? All right? Where's PR2? I have to draw PR2 here. It has to be here. Oh, sorry. It has to be here. It has to be aligned. Why? Am I toggling this LSB? Am I toggling it? Am I toggling this guy? Am I toggling it? Can I toggle it? It's a static register. It's a constant. I read a constant to it. I'm not toggling it, right? Which is being toggled? The timer. The timer's numbers is being toggled. And this is toggled at 64 megahertz if you have a 1-to-1 prescaler. And this is being toggled at 16 megahertz if it's a 1-to-1 prescaler, okay? If you change it, both are changed. Important, okay? Keep in mind. If I change the prescaler, both are changed at the same time. Why? Because they both use this frequency on the top. Okay? And here's important, aligned with the 8 bits. Not here. So, if I give you a number in PR2, 63, for example, I put in there. How long it takes to match this number in order to do something with the PWM. That's a register the timer 2 is trying to match, right? Starting from 0. Counting from 0. And then when it matches whatever number stored in PR2, it do something. We don't worry about what are the actions now. But I'm just asking how long it takes to match this number.
63 over 16.
63 counts.
16 3 counts. However, in the on the data sheet, it plus the 1. It plus 1 to it. It's okay, but it's not a big change. So it's PR2 plus 1. And then what? That's the counts, right? That's the counts. That's the counts. Don't worry about the plus 1. I don't know why, but let's just use PR2 plus 1 for now, okay? It's not a big change. So let's just assume it's this many counts, okay? How long it takes?
That over 16 mega.
Divided by what? If you are given with a count to find out the time, right? That's just one of the 2 problems we have been dealing with all the time. If you are given, divided by what? Divided by the frequency, right? So you can flip that second, the time. So it's giving the time. Divided by what?
16
All right? What is this giving you eventually? The time, the period. What's the period of the PWM? The whole thing here, right? Okay? So that's the first thing you just have to know, have to master. Otherwise, you are losing like 40 to 50 points on the exam. It's just one simple equation. Middle school level math.
We just have to remember the plus 1.
Yeah, remember the plus 1. That's the equation. You just have to use it. Okay?
So plus 1.
If I'm telling you FOSC on the pick like some other platform, this is 100 megahertz. Can I still do it?
Yeah.
Yeah? What is this?
100 over
FOSC divided by 4 divided by prescaler, right?
4. Yeah.
You can always make it right. Any questions on this? What's that?
Oh, how do we apply this formula?
How?
Yeah, like
Just
when-
plug in, for example, this number is given, just plug it in.
So when, what is it solved for?
What's it solve for? Solve for the period for the PWM wave. Yeah. Don't lose any points on this, right? If you don't understand it, just ask your peers. What's that?
Wouldn't FOSC over 4 3 give us the frequency to go through its own?
Yeah, it's just being divided by 4 times on the hot wire. The digital designers designed it that way.
Right, yeah, I'm just saying like the equation FOSC over 4.
Yeah.
Divided by 3.
Yes. Yeah.
Yeah.
Yeah. This one is FOC over 4 divided by prescaler.
And
Because that's a real frequency toggling this bit. This makes perfect sense, right? That's exactly the frequency over here toggling this LSB.
Yeah.
Toggle once, flip once, count by 1. That's it. You got this many counts, just divided by this frequency. You got a time.
So does the prescaler have to be a power of 2 then, since it's done with that kind of?
No, they designed it that way.
Okay.
It's customizable. You can do a 1-to-2 prescaler if you want. It's not just not a big change. That's why probably the designer didn't do it in microchip. They have 1-to-1, 1-to-4, 1-to-16, but definitely you can have like 1-to-2, 1-to-8. I think Arduino's have 1-to-8 sometimes, if I'm right. It's okay. It's all right. But for this timer, we're only using 1-to-2, 1-to-4, 1-to-16, but no other prescalers, right? Anything else here? Is that clear on PR2 calculations? So why we need that? Why do we use PWM? You know it's useful, right? You can, turn on an LED, dim it, make different brightness. You can also use this pulse to control what? Motors, DC motors, right? Same concept. You can control the speed
The DC voltage.
very accurately, actually, and give a feedback, And stepper motors, like windshield wipers, right? Stepper motor. maybe even speaker as well, right? A lot of things. So whenever so in the real world, right? So you are a digital engineer trying to create a pulse, series of pulses or waveform to control things like motors or LEDs. What are the two parameters you need to know?
The time.
Period and duty, right? So the PR2 stuff, that's a good question over there. The PR2 stuff, everything on this page, solves this problem. One of the two parameters. Done. The next step is going to be this one. Okay? If you know the period, you know the duty, you know everything. That's the nice thing about digital, right? It's so simple. You don't think that way? Any questions on this? Just record it. Okay, you can always come back to the video and look at the notes. And ask your friends if you still don't understand it. 20 points, 30 points on the exam. Oh, there are totally 10 problems and 10 points for each. Okay? Now let's tackle this. Duty. Duty cycle. Duty cycle is a percentage. Okay? That's the 2 bits. That's a bit. Does PR2 has another 2 bits over here? Why?
Because that's what we're
It's an 8-bit register. CCPR1L DC1B 8-bit 8 bits 2 bits CCPR1H No, it doesn't compare. It doesn't. It compare with this guy. So looking at the drawing here, this happens. It's also gonna take this down here. It's not concatenating to it, but actually it's using these 2 bits as well. When this happens, when PR timer 2 equals PR2.
It pushes the low bits in from L.
Yeah, it sends it in whenever that equals that. So another question here is when timer 2. Oh, that's probably why. I'll talk about that later since I didn't design the the hardware here. It's like taking one more cycle here. Is that why PR2 plus 1? I don't know. Who knows? We don't care. So timer 2 equals PR2. It says on the data sheet it equals PR2. It didn't say PR2 plus 1. That's interesting. So let's assume it's because it's not a huge difference. Let's just ignore that for now, okay? So when timer 2 equals PR2, what are the actions is being taken here? So just look at the waveform, right? So that's PR2's counts. Whenever it reaches here, what are the actions? CCP1, yeah. Give a 1 to CCP1. That's a pin, right? That's a pin. It's a pin here. Give a 1 to it. Make sense? What else? Timer 2 clear? Clearing timer 2 or not? Or no? Here, do you need to clear timer 2?
It needs to stay counting, right? So you can get the duty value or no?
So here, right? So it counts to here, then you do something to define the duty cycle, right? Then it keeps counting until here, you get a PR2, and then you keep it high, you send this high, and then you need to start counting from 0 because you have to get another PR2 cycle, right? So this must be cleared. Timer 2 has to be cleared. Another silly question. Clear where? Clear here or clear here? Yeah. It's one counter chain. If you have designed counter before, have you in digital logic or somewhere else? In like IPGAs? Okay? Counter just one chain of D flip-flops. So it uses the output of this D flip-flop. Use the output, the Q here, as a clock for the next stage. Not D. So D is not being used, it's a clock. So the Q from the first stage is used as a clock, as a second stage. It's a chain. How can you control that? This is clear, this is not. It's all cleared.
Yeah.
Everything is cleared. Okay? That's why I call it a silly question. It's all cleared. Timer 2, everything, the 10 bits, 0. Another action is load CCPR1L to CCPR1H. Why? Whenever it's being stored here, it's not being used as a duty value. But whenever it's reaching here, you know that you need to use that value to define this period now. So you just load it here and start using that. Why you have to load it here? I think it's probably trying to avoid any interference or anything. I don't know, since I cannot see the inter-circuit design at the transistor level. But however, you need to know that whenever it reaches here, it's going to load whatever being put in here to here. And you are still using these 2 bits to form a 10-bit. It's a 10-bit number. Important, okay? You have to know this. 10 bits. If you just look at other materials on other websites, this probably didn't tell you the details here. However, super important to get it right on the exam.
What is the DC1B?
Yeah, it's 2 bits in the con register, in the control register, somewhere else. It's just using these 2 bits to form a 10-bit number. You don't have to worry about it. It's just 2 other bits somewhere else. It's just a storing of value. It's okay. I'm taking these 2 bits somewhere else to form a 10-bit number, right? Just 10-bit number.
Do you know what CCPR stands for?
Compare capture PWM register number 1 higher byte.
Okay.
Oh, I'm too fast. Let's do it. Compare. Remember, it's
So
2.
can you go through one more time an example of this system working, just like
Yeah.
one cycle of it? Like,
Yeah. Sure. Yeah.
Sorry.
No problem.
Not that page. The
Which
next
one?
with the
Yeah.
forward.
Here.
That. Yeah.
Okay. This is a register that stores the duty value. It's just the 8-bit D flip-flops actually, just a register. So registers can store numbers, right? It's a latch. Can latch a digital value in there, no problem, right? Okay? This is also a register. It's a higher byte version of it. It's just a similar serving for similar purposes. However, we don't have to know the details. They are both 8-bit registers. It's just one clock cycle. You can send everything to here. Just one clock cycle. Okay? These are another 2 bits. The 2 bits. It's being used as a lower 2 bits for the whole 10-bit number. Why? Because it's designed that way. Why you have to use 10 bits? It's trying to give you a higher resolution for the duty cycle. We'll see the details in a bit, okay? We'll see the details really quick. It's just a 10-bit number that defines the duty cycle. That's it. So what's the register defines the period?
PR2.
PR2 here. Done. I told you, done. This page that defines the period is done. Now we come down here for the duty cycle because we just need to know the period and the duty cycle to define everything. Clear? Cool.
Why do you need the second 8-bit register
Here?
to define the duty cycle if it's a 10-bit number for the duty cycle? Yeah.
You mean the second here?
Yeah.
It's like I said, I don't know the details of the digital circuit design. However, what's defined here is whenever the timer 2 matches this number after the period, whenever it's trying to start a new cycle, it's sending this duty value into this register and use it for the duty cycle. So this is like a being used, right? This is like a preparing it because in the C code you do all these like mask, ORing, like sending, assigning. I'm thinking probably it's interfering with something. I mean, with all the operations, the digital blocks. Actually, I did the same thing actually in my digital design. I usually have all the whatever the registers, working with the other parts of the digital block before a latch. So you know whenever it's all ready, you send the 1 clock and send it out. So it's not interfering with whatever in here, okay? Usually that's the way to do it. And I think that's probably the same serving the same goal here. You store that duty cycle value here, you can write it in here in this register. That's a register, so you can write into it, right? So you use the C code to write that value into that register, okay? And then it's going to automatically doing that for you. You don't have to worry about that. However, the important thing is this LSB here is aligning with this LSB. New thing, okay? It's not. I recorded. You watched it, but I recorded on the video after the lecture on Friday, and it's now on Dr. Costin's website. It's nowhere else. I searched online. There was one guy explaining why they use DC1B. It's the only video I found, but he was saying he sees something weird on the oscilloscope. I didn't know what's going on, so I was not able to find out any tutorials or documents explaining this online. But now let's get into it. What's really happening is you are toggling this guy at what frequency?
64 mega.
FOIC, right? And this is aligned with this one. Am I toggling this LSB? Same question, same silly question. How can you toggle a register? It's just a constant. You write into it, okay? Stores the value, will give you that duty cycle. What you are toggling is a counter. You can design a counter digitally. It's just a chain of D flip-flops. And this one is being toggled, and it's aligned with this LSB. Okay? That's important. Why? Because if I give you a number, for example, I give you a number here that as a duty value, 100, just a decimal number, 10 based. Tell me if it's a 1-to-1 prescaler. What's the duty cycle? What is the duty cycle here?
100 over 255 times 100%.
Yeah, that's the count. So there's no +1 like the PR2 have a +1. This one doesn't have a +1. Keep in mind, okay? It doesn't have a +1. The count. This is the count. This is the count you're putting here, 10 bits. So convert this one into a 10-bit binary number. That's a count. If you are given with the counts to find out the time, what do you do? Divide by what? The frequency. So what's the frequency of the timer being used to reach that count? FOIC. It's not FOIC divided by 4 anymore. No, it's not. See? Here, this LSB is being toggled at FOIC, not FOIC divided by 4. Does that make sense?
I've got a question. Can you go to the other page real quick? So over here we're comparing, because I understand that we're FOSC is the rate at which like the least significant bit is toggling at, right?
Yeah.
But the place that like we're reading from the timer, like the part of the timer that we're reading from is the like third bit that's toggling at FOSC over 4. So if that's like the bit that we're reading from and toggling from, like that's what's being compared to like CCPR1L.
No. Oh, yes. Because these two are aligned as well. It's okay. Who cares? This one is toggled at 4 times faster.
Yeah.
Until like 4 cycles, it got this toggle at once. Yeah.
And I get that, but aren't we writing like our duty value into CCPR1H?
No. That's why
I
people
see.
are got confused.
Okay.
That's why from other websites you got the wrong numbers.
So
That's
you're-
why I got confused as well for on Friday. This one will be written here,
Okay.
not here.
So it's being written there.
Yeah.
Then how? So
Let's do it.
okay.
100 counts divided by what?
Then it's not- our timer is-
Keep in mind, if you see this on the exam, if I give you a duty value, a number in decimal, how do you find out the time?
Divided by 64
It
megabytes.
has to be 4 times faster, okay? Not the 16 mega.
So the duty value is not the actual duty value that we want. It's like the duty value that we have to put into this register to get a different time.
Yeah. Don't have any bias on these 2 bits. They are just normal 2 bits. Same D flip-flops on the chip. So whenever this number is being put in here, it's just being put in here, starting from this LSB, not here. You are thinking about, hey, whenever this one reaches this PR2 number, the whole thing, the whole 8 bits is being sent to here, and this is being used to compare with the timer. No, what is being used to compare with the timer? This. Or you can say, hey, these 8 bits is comparing with this. It's also fine. It's okay. No. Whenever you got non-zero, if these are not 2 ones, they are different. You have to fully finish these 2 counts here. So let's just use these, matching these. What's that?
So for the duty value, could we just throw in something that had 2 zeros and then the 8-bit number
Yes.
that we actually wanted?
Whatever number. 100, I don't even know what are the lower 2 bits are. I don't even care. Why do you care? It's just like this decimal will be converted into a binary and being placed in here. That's it.
So they're just functioning like 10-bit registers and 10-bit.
Yeah.
Like, so okay.
It's with a different frequency.
With a different frequency.
Yeah.
Okay.
Who had a question? You?
You kind of answered
Oh, cool.
it. Sorry.
No problem.
So when we're getting like PWM duties, like duty value like questions, right? We're treating them as 10-bit timers and registers, and with 64 mega like counting timers.
Yeah.
Awesome.
Clear?
Yeah.
It's recorded, and I think you are sitting pretty close to the microphone here, so it's
Oh.
recorded as well. You can hear the question in the video. If you are still confused on that, revisit the video, look at the notes, do the calculations. How did I know that is right?
Data sheet.
Google.
What's the prescriptor we use in the lab?
101.
No, what's the prescriptor we use in the lab?
FOSC over 4.
Yeah, no, that's not a prescriptor. That's
That's
yeah,
a timer.
yeah. What's that?
16.
1 to the 16, right? So what's the real frequency here?
4.
Divided by 16.
Right? That's a prescaler. So what's the real frequency toggling this LSB for the timer tool we used?
Can you use 1 to 1?
That's not important though. Whatever. Okay.
Gotcha.
All right. Then what? Every count takes how long? 1 over what? How long is it? 0.25 what? Do you agree with that? And what is that? What kind of other question I can ask? What's the resolution of the duty cycle you can adjust? What's the resolution? What does that mean? I can only change like 1 count, 2 counts. Can I do like 0.5 counts and 2.5 counts? So what's the resolution? 1 count. How long it takes for 1 count? Duty cycle is what? Time, right? So duty value is the time. Okay? So 1 count is how long? It's given. It's how long? So what's the resolution of the duty cycle adjustment? Quarter microsecond. Agree with that?
That's the duty cycle resolution?
Yeah.
Yes, that is what
And
we
for
got.
that, we'd be given that there's a 1 to 16 prescaler.
Yes.
Okay.
All right. Remember last week I used whatever in lab code 0xFF. So what is 0xFF? 255. Can 255 fully turn it off?
No.
It didn't turn it off. It's missing 1 count. So 1 count takes how long? A quarter microsecond. Look at it. Look at it. The bias time. Moment of truth. What's the division? 1 microsecond per division. How many? 1, 2, 3, 4. A quarter of microsecond. 1 single count. Didn't turn it off. A lot of people will tell you it's a hardware issue. LED is not fully off because of the hardware issue. Is it?
No.
How do you want to turn it off? Add 1. What's the value to turn it off? 256.
So then
Okay.
we would want to add 1 to everything then, right?
Just add to this. Why everything?
If we want the real color.
Yeah, so it's gonna be, so if you look at the cube, right? Got the cube on Dr. Carlson's website. Here is actually wrong.
256.
Yeah? So you ask a question, what about 0? You're trying to think about, is 0 really 0? Because we have 255, it's not really 255. Is 0 really 0? Yes, 0 is still 0. Okay? No problem on that. Any questions on this?
How would you pass in 256 if you only have an 8-bit?
It's not 8 bit, it's 10 bits.
That's true.
That's the whole point. Okay?
Okay.
So just treat them as 10 bits. Work
Mhm.
on 64 meg.
Yeah.
Sounds good to me.
So you're thinking, previously we had a question, right? This is 10 bits. For this one, you have 10 bits. And this one, PR2 is 8 bits. How that works? Your duty value is longer than your pre-period. Is that true? Why it's not true? Remember last Friday we were talking about, hey, PR2 is only 8 bits. 8 bits has 8 bits count, like 255 counts. It's defining the period. Definitely the period is usually longer than the duty cycle. So, but however, you don't have 8 bits here, but you have 10 bits here. Is that true? No. How many bits do you have for PR2? It's still 8 bits, but it's okay. Why? Because it's shifted by the left by 2 bits. It's matching with the 8 bits, upper 8 bits here, not these 2. If you compare the whole thing, they are both 10 bits. They are both 10 bits.
You're just not worrying about the first 2 bits.
Yeah, they are the same length. No problem at all. Same length. So for the period or this duty cycle, it's the same. The timer and the duty cycle is the same length. No difference. So if you have a 0 here, you have 0 here. You put a 0 in here. What are you getting here? You don't even need to count. The timer 2 starts with 0. It's gonna be 0. Why you're getting 0? Use the equation. 0 counts divided by what? You don't even need to care. It's 0, 0. Yes, right?
So anything other than 0 would be that plus 1.
It's just the full counts is 256. That's the only thing you need to know, I think, for now.
Okay.
Right? Okay. It's about the time. I think this covers probably 50% of the problems. and I'll cover the other 50% on Wednesday. But definitely, I think you have a lot of things to digest or to learn. Take the time, go through this today, and see you on Wednesday.
Thank you, Professor.
Sure.